Welcome, thank you. Start off with thank you for joining in today. As Francisco said, my name is Ben Zemansky. I'm a structural engineer with WSP Parsons Brinkerhoff. I have about 9 years experience in the field of bridge engineering. I've been involved in design, analysis, inspection, load rating, so forth. So today my topic will be computer analysis, verification, and validation. So when I was deciding on a topic to cover, I decided I wanted to choose something that was a little bit more broad in order to offer some support for the biggest range of engineers as I could that are involved in modeling. So I find a lot of times when we have engineering discussions, we can get very specific, which is definitely interesting, but it's not always applicable to everyone. So my topic today will be fairly broad and hopefully will leave you with at least one piece of useful information for anyone tuning in today. Okay, so I'll start today with a quote from Stan Caldwell from Structure Magazine. And what he said was, if you're not able to roughly design your structure by hand, you certainly have no business relying on your computer to do so. So basically, this is going to serve as the framework for today's presentation. So what do I mean by this? What does he mean by this? What he's talking about is understanding your structure even before you start modeling it. So computer analysis is a very useful, powerful tool, but it's only a starting point. So you really need to have an understanding for the structure that you're modeling prior to ever opening the program. So you really need to have an idea of what your results should be, what you're hoping to get out of the program, and exactly how the structure should be behaving. So while it's a powerful tool, you really need to have an understanding of your structure prior to even beginning. So this is pretty much a summation of what will be discussed today. Okay, so I'll run through my overview. Basically today we're going to be talking about setting up your model, and this might be the most important step that you'll go through because it's going to serve as a foundation, no pun intended, for your analysis. This step is also so critical because at this point you'll begin documenting your model and start setting up the framework for your model going forward. So this is where your best practices are going to start and where you're going to start documenting what you're putting into your model and all of your assumptions. So it's absolutely critical to think about what's expected from your model and what might be expected in the future. A lot of times you work on a project and build a model for a specific function and you end up having to solve a lot of problems. Specifically, like if it goes to construction, you might need to go and keep coming back to that model and do different things with it. So you need to have some forethought. Next, we'll be talking about debugging your structure. So this is the point after you initially set up your model, you run it for the first time, and you're starting to resolve any errors, warnings, or anything else that's obviously wrong and that's not expected. So as diligent as you might be in meticulously setting up your model, almost always you'll need to go through the process and get your model running correctly. So next, moving on to the topic of the presentation, is the validation process. So at this step, this is where you'll take a step back, look at the big picture, and think critically of whether or not your model is making sense. At this point in the presentation, I'll run through some tips and tricks that you can use to validate your model, and we can talk about some key things that you want to check to quickly and easily confirm that your model is giving you good results. Next, I'll go through a troubleshooting process because even the best model can run into problems, especially the larger your model and the more complicated it gets. So we'll run through some common problems and how to fix them. Also, many of the problems that you run into you'll find are relatively simple, but in some cases it can take half a day to a day to pinpoint. So this is where knowing where some of the sources of error can come from can save you some time. So I hope I can help you out there. And then finally, I'll run through our best practices for setting up your model, steps you can take, methodologies, and things that you should do in order to have a properly running model and just overall best practices. So, okay, moving on. So, model setup. So starting off, I'll start off with some tips that have worked best for me in my experience thus far as an engineer. first things first, naming your model. Your naming convention should be very descriptive. It should include the date the file was created and a good description of what you're modeling. So the current version of Windows, I think you can have quite a long file naming path and file name and file path. So you should be able to take advantage of that. Be descriptive, because further down the road, when you're taking a look at it, or when others are trying to check your model, they're going to be, it'll be very helpful to know what exactly is in your model. So the dead load model, say just that. Also, you're going to want to create a save as of your model as often as possible. This is very helpful. I've particularly been helped by this, where creating a save as of my model when I go and have a large increment in what I'm putting into it, the loading types, the analysis type. It's very helpful to go and constantly save a version, because that you can always go back and revert to a version that you know is good and is running properly. Because remember, computer memory nowadays is very cheap, and your salary is not. So just consider that. So you can always go back as needed. Another thing, this might not be true for you, but it's certainly for me, is that I find that my model will run many times faster from my local C drive than from a network drive and even my external hard drive. So it might not be for you, but it's particularly true for me, so give that a try. But always remember to back up to your network drive, to your project folder on a regular basis, because you don't want stuff stuck on your hard drive and then have your hard drive crash. So also, it's good practice to always keep a master version of your analysis, and this includes everything that's in your model. So you're including all of your dead load, your live load, your wind loading if that's something specific, seismic loading. That way you have everything all in one place, and you make sure that that's always the most up-to-date version. And then from there you can always break off and create other versions. So specifically, you're going to want to break out your model for moving load analysis or seismic analysis. These are types of analysis where it's very taxing on your computer. It'll take up a lot of RAM, and if you can minimize the number of load cases, then that's even better, because sometimes I've had issues like from my laptop where it hasn't run properly because I have too many load cases. I'm trying to run all this fancy analysis. So another thing to keep in mind is your format of your numbering and your elements and your loading should be as simple as possible. So start off, before you even do anything, of getting all of your thought processes on paper. MIDAS allows you to have 6 characters for your elements, so you can use those to define what each of your element types or your loading types mean, so that in the long run, in the end, when you're starting to pull results, you can quickly and easily lump results together, and you know what you're looking at before you even looked at the user interface in the model. So right off the bat, establish a node member loading convention. You can do that all on paper, or you can do that in your Excel spreadsheet. So another thing that you should keep in mind, this is also, I'll say this over and over again, is keep everything as simple as possible. You want to minimize the number of joints. You don't want extra joints. But you also need to keep in mind that you might need to get forces at certain locations. So while you're trying to minimize the number of joints you have in your model, also keep in mind that where you might want to pull results from. So for instance, you'd want, where is the location where you're going to find your maximum positive bending or your maximum negative bending or your shear force. So just think about that, and then you can locate nodes in those places. So I included a little sketch here of something that I commonly do when I set up a model. And you can use a plan drawing if one exists, or if not, if you're at the point of still design, that you might want to do a hand sketch to scale to make sure that you can properly lay out your nodes and your elements. So I just included here a simple tier with my node and element layout. You can do this once and then use this as a convention throughout, and with one digit changing for the peer number. So it's as simple as that. And I found that this is also true in design, that it's a good idea to go and get your a sketch to scale on paper so that you can see if your design makes sense. Because you'll find out right away if your sketch doesn't look quite right and it's drawn to scale, it probably isn't right. So this is true in both analysis and design. It's a good idea to get everything to scale and get it sketched out. Okay, so setting up your spreadsheet. There's different ways that you can go about setting up your model. One of them that I usually like to do is to do everything in a spreadsheet and use that as the basis. So in almost every situation, your geometry or loading will change, so that's where it's particularly useful to use a spreadsheet to go and keep all of your information and have everything updated through there and then imported into Midas. So this isn't necessarily true in every case. You'll have situations where, let's say you're looking at a temporary condition in the field for construction or just something quick that you're looking at. In that case, you can also create a import a DXF AutoCAD file, and that way you can quickly import your geometry that way, or you can just use the user interface. I've done both of those. In any case, make sure that if you've got a large model and you can see where you're going to have things change going forward, that you have everything future-proof, meaning that you set up your spreadsheet so everything is linked throughout, and a simple few changes to a couple entries and everything gets updated. So remember to future-proof your work. The other thing is, I'll talk about this quite a lot, is make sure that you are constantly documenting all of your methodologies, your inputs, particularly your loading input. You can do that either within a spreadsheet, which is useful if you're using a spreadsheet for your input, or just with simple hand calculations. So that's important, documentation. The other thing is, I find it useful to break out each of my loading types so that I can easily identify where each loading is coming from. So some people would prefer just to add into their model simple, the AASHTO loading convention DC1, DC2, DW. But I find it particularly useful, even though it increases the number of load cases you have and increases runtime, to break out each loading type, because you can tell exactly where each load is coming from, and you can always create a load combination further down the line. So let's say that you're using a spreadsheet to set up your model. You can easily do this to create your nodes, your members, plates, section properties, loading, whatever it may be. And just like when you go and create your model, your spreadsheet should be named similarly, that you show your date and a good description. Usually you're going to want to name your spreadsheet similar to the naming of your model. That way you know to go together. So in order to define your geometry, what I usually do is I get the horizontal curves, vertical profiles, super elevations, cross slopes, so forth from the civil guides. I put that directly into my model, and then everything is linked to those values so that it's very simple input. And then going forward, that if any of those values change, your stationing changes, the curves change a bit, you can always just type that in, and everything else through the rest of your spreadsheet will follow. Because chances are it will happen. I think it's happened on almost every project I've ever worked on. The other beauty of using a spreadsheet is that, like I just said, you can link it throughout. That way the changes carry through. And also you can add certain checks off to the side in parallel to your elements and your section properties, so that you can find out what you're actually putting in the model as far as your structure weights and your section properties, and then have right next to there your hand check showing whether or not what you're putting in is what it really should be. So that's the beauty of using a spreadsheet as well. So how do you go and take that data and put it into Midas? So a couple ways you can do it. You can export an MCB file, which is just the text version of your model, or you can use MCT command shell, which is also another useful tool built into Midas that allows you to input your text data piece by piece, and that's basically like input all of your nodes, input all of your elements, your load combinations, whatever it may be. So that's also a useful tool. I also find I'll use MCD command shell where the geometry will update and I know nothing else changes. So all I need to really update is my node locations. So I just paste that in, run it, and everything carries forward. So these are very useful tools. But one of the beauties of using a program like Midas is that the user interface is very powerful. So after you input your text data, you can go back into the user interface, turn on your local axes, and verify all of your members are oriented as you expected them to, and that you can look at the renderings to see that everything is oriented and the sections are exactly as you imagine they would be. And because you're going to find that later on, it's very important to make sure all of your member rotations are consistent. That way you can pull out your data quickly and compare. Okay, so I'll move on to debugging now. Like I said, even the most carefully set up model can have errors and warnings. So one thing to know is there's a little warning box at the bottom of your screen telling what your errors or your warnings are. And one thing you should know is usually the error that you're getting is not telling you exactly where the error is coming from. For instance, you might be getting the error that you have a joint in your pier cap that's unstable. But the issue isn't with the joint in the pier cap. The issue is because the base of your column, the support is not properly defined. So keep that in mind. Also, you need to know that errors need to be resolved because your program will not run unless you solve all of your errors. Warnings don't necessarily need to be addressed, but you should be aware of what they are and think about if it makes and if they need to be addressed or not. So I'll go through a couple common sources of error that I've frequently come across. One of them is boundary conditions. You'll find this quite often, and this will affect your structure stability. So verify that all of your supports are defined properly, that you have all your supports in the right locations, and this kind of goes back to the quote at the beginning where you need to understand your structure before you begin to run your model. So make sure you have all your supports defined correctly and your load path is as you meant it to be. So another issue I've had is members are defined incorrectly. So you might have in your spreadsheet, you're defining your members and associating it with importing this data. And you'll find that for whatever reason, your members connected to a node you didn't intend it to. Well, you can quickly and easily look at your user interface usually and find out if that's a problem. And then from there, double check your spreadsheet and make sure that that change doesn't carry throughout, because like in the case where you have multiple peers, you might have this problem in every single peer. So make sure the problem's not repetitive and make sure that that doesn't carry down through any other part of your user input. Other places where I've had problems is where I made changes directly through the MCB file or MCT command shell, and I didn't think about where it might affect the rest of the structure. So for instance, in the user interface, I defined tapered section groups for some members, and then I changed, either eliminated a member or whatever it may be, and I'm getting runtime errors. So think about when you're making changes to your text file, you need to think of where else this will affect your model. So rigid links might be the #1 source of error in my experience. So there's a couple different situations where your rigid links might be too stiff. In that case, the model might not even run at all. I've had that issue. So generally, rule of thumb is your stiffness of your rigid link that you're creating should be about 10 to the 3rd times stiffer than the stiffest member it's connected to. So that's in the case if you're defining your rigid link as a custom member, like I have shown here. Another situation is that your rigid links might be too soft. I've also come across that, and that may not be flagged as a problem, but you'll probably see, based on your deflections and your displacements, that something isn't quite right. So that might be the source of error. So beyond just runtime errors where flagging you, telling you that something isn't quite right. There are also maybe issues with your rigid links that are just straight up causing incorrect results. So look at your structure and think about if it's making sense. As far as rigid links go, like for instance with bearing members, a lot of times I'll use rigid links to define a bearing member, and depending on your stiffness, you could have results that don't make sense. So for instance, recently I was working on a curved girder bridge, actually in another program, and I was noticing that my bearing forces didn't look correct whatsoever, and I found that you basically need to iterate your structure, iterate your rigid links to find what the proper stiffness should be. And that kind of goes back to the fact that modeling is a tool, and you need to understand what results you should be getting out. Okay, so moving on to basically the topic of the presentation, the validation process. So what do I mean by validation process? I mean making sure that your model is producing good results. So you need to have an idea of what to expect from your model and how for it to behave. So I've said this already, that the computer model is a tool, and it's not the end-all be-all. Are your results making sense? And it always goes back to the old saying, garbage in, garbage out. So think critically. You can be brilliant and still make mistakes, and you can be brilliant and not totally think about the big picture, and that's what it's all about, is the big picture. So I'll go into detail a little bit more about model validation and things that you can do depending on loading type. So we'll start off with dead loads. Usually dead loads is a good idea to validate your model in the dead loading as like first step, because usually the results are fairly simple and it's easy to trace the load path. So some things that you can do basically is you would do some hand calculations, or you already have it built into your Excel, and verify your reactions, verify model weight, and then you compare that to what you're getting out of the model. I've got a little hand back of the envelope calculation off to the right here showing just a simple calculation for calculating like a pier weight. So things like that, very simple, quick calculations to see if your model is making sense. Another thing that you might want to do is you can either do a save as or create a temporary load case where you add like a temporary load, like 1,000 kips or something, and stick it into a location where you know that you can verify that that load is getting down to your supports and the load path is as you expected. So that's something else that I'll frequently do. And then once I verify that it's correct, I can delete it out. But it's also a good idea to document that you check that and that it makes sense. The other thing, too, is to check that your magnitude and the direction of the forces and the reactions that you have are making sense. So, for instance, if you've got all vertical dead load on a pier and you're seeing very large longitudinal forces, chances are something is not quite right in the input. I had a situation recently where I added all my forces and I accidentally defined a point load as being along a local axis instead of global, and then I was getting very large longitudinal forces. So that's another area where you can look at your user interface and double check to make sure everything's making sense. But just look at the very simple things, look at your reactions, make sure everything makes sense and the load path looks like it's correct. Another place to look is your deflected shape. So start thinking about, is your model and deflecting as you expect? What are the magnitudes? You can turn on your legend or in the user interface quickly just look at what the magnitude of your deflections are. If you're seeing you've got a couple feet of deflection in the simple multi-girder bridge, chances are you don't have something defined quite right. You probably have a stiffness off in your superstructure, your rigid links, or whatever. Another place to go and identify where if you're getting funny deflections is to look at each load type. Like I said, it's nice to go and break out each load type, your wearing surface load, your pedestrian rail, your self-weight. Break that all out, and then also within Excel you can go and overlay those, superimpose them onto each other to see what the contribution is from each and see if you have something that might not be quite right. Okay, so looking at live load. So as always, document the whole way through. So get each of your live load cases on paper, the locations of where each lane will be, and make sure you have all that down on paper before you go and define your moving load cases. So some things that you can do to verify that your moving load, your live load is functioning properly is there's a couple tools within Midas. One of them is Moving Load Tracer. I have a picture right here of actually of an HL93 loading. And this is where I'm asking for where's the location of the truck and lane for the maximum force in that column of that Pier 1 there. So this is a very useful tool to tell that the point loads are moving to where you think they'll go. The other thing is you can look at your influence surfaces and influence lines to see where the largest contribution is for whatever location you're looking at for the force. So make sure that the model is functioning properly and the live load is where you expect it to be. And in order to validate your live load, you're probably going to want to check a few key locations. For instance, your maximum negative bending, maximum positive bending in your girders, the maximum reaction at a pier, and so forth. And then some tools that you can use for verifying your live load. You can just use the tables that are provided in the AISC Manual of Steel Construction, the continuous beam tables. Also, there's this older document which I find quite useful, and I also use it for some quick live load checks, is the AISC moment shears and reactions for continuous bridge booklet, and I believe you can get that free online. So these are a couple valuable tools that you can use to quickly verify that the loading that you're getting in your model is correct. Okay, so what can you do to verify that your seismic model is correct? So the first thing I'd say, very important, to look at your mode shapes. At least the first 10 mode shapes to see that the shapes make sense and that your natural frequency and the period of your structure looks reasonable for the type of structure that it is. If you've got an extremely high period, you might not have something defined quite right. And this is true even for if you're not doing a seismic model. Even if it's just a dead load model, you can look at run an eigenvalue analysis and see if your fundamental period and frequency look reasonable. So I would say do this after each time you update your model. I've found that that's quite helpful. And usually the other thing too is that you'd want to look at your mass participation. Generally over 90% mass participation in the horizontal directions is good, above 80% in the vertical. And then as far as hand calculations to verify your seismic loading, you can spot check, look at your piers, for instance, and do hand calculations. And you can use just like the single mode spectral method that's within AASHTO, and use your response spectrum function to go and find out how much of your load is being transferred horizontally. So quick and easy things on a single sheet of paper to go and verify if your seismic loading is correct. All right, so moving on to troubleshooting. Just with debugging, like I said, even the most meticulously set up model, you can have issues where you're not getting results that look quite right. So I'll run through a couple cases similar to what we just did and break it out by loading type. So looking at dead loads, you might have a situation where your weight doesn't match your hand calculations. So in that case, just make sure, verify that your self-weight is checked off. You have your self-weight included. You have all of your applied loads that aren't included in the self-weight all accounted for, and you should be able to quickly and easily do that because you've already documented that. So just check back and make sure all of your weights are accounted for. The other thing too is check your material densities. I know it's nice that, like for instance, Midas will have a drop-down. You can select that you're using, your member is steel, and that it's A36 or whatnot, and then automatically there's presets for your modulus of elasticity or weight density and whatnot. But don't always take that for granted, and always verify that what you have in the model is correct. So you verify that your densities are correct. That's certainly a spot where you might run into a problem. Also, you might have an issue where you've got very large deflections. So usually, like I said, it always goes back to rigid length. So make sure your rigid lengths are defined properly. Check that your member releases are defined properly. And you can easily do that by looking at your model through the user interface. Okay, so issues you might run into for live load. You might find that your results that you're getting for your forces don't seem quite right based on your hand calculations. So a couple of things, just check was your multiple presence defined properly. It automatically is in the program when you define a moving load, but you can also manually change that. So just make sure that's defined properly. You can manually define your impact. Is that properly defined? Is your combinations of your trucks with your lanes defined properly? There's a couple ways to define it, whether they're combined or they're independent of one another, so look at that. And then, as always, look at the moving load tracer. Make sure that the moving load is moving as you anticipated. So the other thing that you can do just to keep it simple and figure out if your live load is correct is you can go and create a simple static load case with point loads representing each of your axles or your tires, and stick those in key locations to verify that your live load is producing the forces that you expect. Okay, issues that you might have with seismic analysis. So you might have a case where your mass participation is very low. Simple fix would be to increase the number of modes that you're running, but you might have situations where no matter how many modes you run, you still have low mass participation. So I've run into this problem. It seems silly enough, but I've run into this problem a couple times where I'll forget to go into the structure type pull down within MIDAS and say convert self-weight to mass. So that's important that you have that checked off, or else all of your mass won't be accounted for in your model. Also verify that you might have a different way that you go about it, but generally I use the loads to mass function, so it turns all of your loads into masses so that those can be accounted for during your seismic analysis. So make sure that all of those are accounted for. Another situation you might find yourself in is that your fundamental period is unreasonably high. So a couple things to check. Check your member connectivity, make sure your members are connected properly, you don't have any stray members or stray nodes. Check your support definitions, make sure all of your supports are defined properly and fixed against rotation or force in each direction that you assume. Check your member releases. A lot of times you'll have a problem there. And then check your rigid links or your general links. Sometimes you might use general links to go and link to your superstructure. So check to make sure that it's not unreasonably soft or stiff. I have a little image here. This is like a general link definition. So just make sure that that's correct. So when you find yourself in a problem, a good idea to do is to first do a save as of this model, and then start breaking it down piece by piece, starting off with where you immediately think the problem's coming from. So break it down and simplify it, and that way you're able to pinpoint where the problem's coming from. So like a lot of times you might have a problem. It doesn't seem like it's coming from the live load, so take the live load completely out. Just look at the dead load version of your model and do a save as that way and run it. And then from there you can look at all of your broken out loads and see what the contribution is from each. And also, as always, do your back of the envelope hand calculations the whole time to go and make sure what you're getting is reasonable. Okay, so I'll talk about some of the best practices I have for you, and hopefully this is helpful in having you create and build a well-running model that's giving you good results. So this is more or less a summation of what I've discussed today. So number one is documentation. This might be the most important, and this should be started before you even begin your model. So start documenting, get your thoughts on paper, add notes, your methodology. Within your documentation, write down what the model is, where it is. This way you'll have an idea of where everything's coming from. Certainly when someone's checking you, or months down the line someone else picks up the model and needs to use it, they know where everything's coming from. This can be very helpful. And you can do this in a variety of ways. You can do it within your spreadsheets. You can do it on paper. Definitely take model screenshots of your results. That's very helpful. So documentation, number one. Number two, back up your work. So constantly save a version. So every time you make a major change, back up your work. Certainly do it on a routine basis, whether it be weekly or I know people that even do it daily. Like I said, memory's cheap, you aren't. So save your model constantly. Also with everything, whether it's your calculations or your model or your input spreadsheet, use descriptive naming and be very descriptive with the methodology you're using. So include the date you created it and a simple description of what the model's doing. Also, future-proof your work. It's easy to modify a spreadsheet. You punch in a few cells and the rest of the spreadsheet updates. So think about how your model might change going forward. Do you think the alignment of your roadway is going to change? Things like that. So it's very easy to modify a spreadsheet. So future-proof your work. Think forward of what might change. And then, as always, you need to have some sort of expected results. So you need to understand what the problem is you're solving. You need to understand structure. So think about what the results are that you expect. And then when you don't get those results, which may be the case, why is it? Not always the case that it's wrong, but you need to critically think about why it doesn't seem quite right, or why you're getting the results that you're getting. So look at the big picture. Hand check all of your work constantly. Back of the envelope calculations, like I said, a single page on paper, build it into your spreadsheet constantly. Hand check your calculations, hand check your model. Finally, validate your model after every major change. Like I said, the mode shapes, looking at your mode shapes is extremely important. I've had an issue even recently where I've made a minor change. I don't think it should affect really the mode shapes at all, and then I look at my seismic analysis and the results seem funny, so I look back at my mode shapes and they're off. So it's very easy just to go run your eigenvalue analysis for a couple mode shapes and then just see what your period is. The other thing that's quick and easy to verify is your reactions and then your deformed shapes. And the deformed shapes, easily just look at your user interface and see if that makes sense. So I thank you, and I hope that I left you with a couple good tips for modeling.